Hello viewers, I welcome you all to the session on chromatography. We have discussed about the principal classification and other aspects of chromatography techniques in our previous modules. So in this particular module, we are going to discuss about the development of chromatograms. There are three methods to develop the chromatogram in a chromatographic separation procedure, and they are frontal development, elution development, and displacement development. What are the principles involved and what are the ways we have to follow during the development of chromatograms by each one of these techniques we will discuss in this module. And we shall have some idea about the stationary and mobile phases, what we will use in liquid chromatography and gas chromatography, and what are the characteristic features that particular stationary phase or mobile phase should exhibit, and all these things we will discuss. And with respect to the solute systems and stationary phase systems, how the relative absorbability will come into play a role, and we shall have some idea about these things also. So, development of chromatograms is very important in order to obtain the information about the analyte which is being separated by a suitable chromatographic technique. Whichever may be the chromatographic technique you are using for the separation process, there must be a method available to develop the chromatogram. So once the chromatographic column is charged, that is, once the column is filled with sample solution from the head, the solutes will be eluted one by one dependent upon their relative affinity towards the stationary phase or their relative ability to get partition between the stationary and mobile phase. So what are the ways to develop the chromatograms after charging the column is very important to understand. So in general, I can say that we will be following a flow chromatographic separation process where the mobile phase will be moving through the chromatographic column. A sample will be dissolved in a suitable solvent. It may be an eluent or it may be a mobile phase. Mobile phase may be a single solvent or mixture of two solvents or mixture of three solvents, whatever it is. So either the sample or the mobile phase or both will be flowing through the chromatographic column. So in this flow chromatography, the effluent will be collected in different fractions, and thus the analytes are going to be detected by inspecting these different fractions which are collected at different intervals of time. So while doing so, how do we collect these different fractions and how the chromatograms are going to be developed? It is very important to understand. The first one is the frontal analysis. So frontal analysis, as the name is implying, the frontal technique will be utilized where the sample solution is passed through an adsorbent, where adsorbent will be activated and which will be used as a stationary phase and which will be present in the chromatographic column. So if you introduce a sample to the chromatographic column, the solutes which are present in the sample are categorized based on their relative adsorbability over the surface of this adsorbent. The solutes which are having greater affinity towards this adsorbent are strongly retained species, and all those solutes which are having very weak adsorption capacity over the surface of this adsorbent are known as weakly adsorbable components. So this is this is the requirement what we should have during the separation of the solutes by chromatographic technique. So we shall classify the analytes as strongly and weakly adsorbable components, and this adsorbability is dependent upon the functional groups, the solute molecules which are carrying, and the interaction, the extent of interaction they are showing with the adsorbent, mostly in the form of hydrogen bonding. So during the elution process, first the pure solvent will be coming out. That's what you will be getting a peak, a small spike in the chromatogram, and that will be for the mobile phase. So there will be a small peak, and that small peak will be certainly for the mobile phase. Then soon after the elution of the mobile phase, the least strongly adsorbed solute will emerge out. Then after the emergence or after the elution of the least strongly adsorbed species, strongly adsorbed species or intermediately adsorbed species will be coming out after the least strongly adsorbed species. Then strongly adsorbed species will be coming at last. And this is the order of elution when we do flow chromatographic separation. So in the chromatographic column, we can see successive plates with additional solute in the effluent means you can have an additional peak in the chromatogram, and that additional peak is for the mobile phase. That's what it will be present in the front of the graphical representation. The front peak is going to be the mobile phase peak. That's what the term is known as frontal analysis. So this additional peak will be giving you the resolution of weakly adsorbed solutes. Are there any weakly adsorbed solutes are present? The weak adsorbability is very high in extent or low in extent. That can be decided by looking onto the order of elution of these weakly adsorbed species. So if we use a shallow bed of the stationary phase and small volume of the mobile phase for the elution process, in order to elute, it may be a mobile phase peak or it may be strongly adsorbable species or weakly adsorbable species, the results are going to be very best. So this type of phenomena we can see in frontal analysis. So in this graphical representation, the percent efficiency of extraction of solutes which are labeled as A and B with respect to volume of effluent which is coming out from the chromatographic column has been detected. When you look at this graphical representation, there are three plates we can see. One additional plate is seen, and that is more particularly for the solvent. So when you collect the fraction of effluents in the flow chromatographic process, the first fraction will be definitely going to be solvent. Then the second fraction, what you are going to inspect will be containing solute A, and which is going to be weakly adsorbed, and at last the strongly adsorbed species will be eluting. On all these empty spherical species which had showed elution from the chromatographic column in the flow chromatography is for solvent, and this dot indicating the solute A which was eluted, and that was identified as weakly adsorbed species, and if there is any strongly adsorbed species, that will be eluting at last. So this is the order we can quote during the frontal analysis and frontal development of chromatograms, in which if there are two solutes, there will be one additional peak will be present as a front. So this peak is for the mobile phase peak. So additional peak will distinguish how many analytes are present. So in order to identify the analyte peaks, the mobile phase peak is very important. That's what the frontal analysis is very essential. So what we do in frontal analysis is that the sample will be loaded into the chromatographic column. Then a fresh volume of the mobile phase will be passed to the chromatographic column. The effluent which is coming out from the chromatographic column will be collected. And if you obtain the detector signal and if you generate the chromatogram, there will be one additional peak we can see as a front. Therefore, this is known as frontal analysis. Then the next one is elution analysis. This elution development of the chromatogram is going to be the most popular one. So what we do here also we will introduce the sample first, then pure solvent will be introduced, or mobile phase is passed through the chromatographic column. Dependent upon the relative migration or differential migration of the solutes in the mobile phase, the solutes are going to be eluted one by one. Here we have to be very careful about the flow rate. Flow rate has to be fixed at the optimum level. Otherwise, the greater flow rate which leads to extrusion of the stationary phase from the chromatographic column or improper interaction of the solute with the stationary phase. Therefore, flow rate is very important. And moreover, the separation in elution analysis is solely dependent upon the partition coefficient or distribution constant of the solute. If the distribution constant Kd is large, then different bands of different components will be separated with more efficiently. So more efficient separation of different compounds is possible whenever its distribution constant is large. So this is going to be the elution analysis. So the following three diagrams are showing a controlled flow and a chromatogram with tailing, and the ideal appearance of the peaks in the chromatogram you can see in this picture. Here there is a controlled flow of the solute through the chromatographic column we can see, and that is dependent upon the relative interaction of the solute with the stationary phase, and if there is any channeling, the width is going to be certainly more, and if the concentration of the solute is more, the height of the peak will be more. If the concentration is lower, the height of the peak will be lesser. So this is going to be the controlled flow. This is going to be the chromatogram we can see under the controlled flow of separation. Means if you adjust the mobile phase velocity to an optimum level, this is going to be the peak we can expect. Here, tailing can be seen. Tailing may be due to certain sites of the stationary phase is retained solutes. So certain group of solutes are retained by certain sites, and where the equilibrium will be disturbed and the partition coefficient will become non-uniform. Therefore, the tailing will be seen, and this is not going to be ideal. This is going to be non-ideal, and this unusual behavior of the solute during the elution process cannot be acceptable. And this is going to be the ideal flow. There is a peak separation, clear peak separation we can see between two peaks. First one solute has been eluted, and after some time like the second solute has been eluted, and there is a clear distinction between peak 1 and peak 2 in this elution analysis. So elution of the solute is properly possible in order to elute solute 1 and solute 2 in a suitable chromatographic procedure. Therefore, according to this pictorial diagram, it is recommended to fix the experimental condition of chromatographic condition in such a way that always we must anticipate the elution of the solute very ideally. If there is any non-ideal elution is seen, it is better to adjust the experimental parameters in such a way that the chromatographic conditions has to be optimized. So it is very important to follow a chromatographic procedure which is more relevant, which is going to yield more accurate and resolve separation for a group of solutes. So it is all dependent upon the flow rate and the partition coefficient of the solute. And the third one is the displacement development. In the displacement development, we will use a displacer, and this displacer will be having greater ability to absorb over the surface of the stationary phase, and this will be introduced along with the sample into the chromatographic column, and the amount of the displacer will be present in very high level. So if you mix a very high concentration of the displacer with the sample, and you introduce the mixture of displacer and the sample to the chromatographic column, then if you do the elution process by passing the fresh volume of the mobile phase, because displacer has the ability to absorb strongly over the surface of the stationary phase, and it will first concentrate at the top of the column. Gradually, the band of the displacer will also come down by increasing its spread, by increasing its weight. So before the displacer, the components move ahead of the displacer. Before the displacer, all the components will start to get eluted because the concentration of the displacer is more, and the density of the band for the displacer is also more. Therefore, the components apart from the displacer will start to getting eluted. So we can see different zones, and these zones will be in the order of their decreasing absorption strength. And what is this absorption strength? Displacer is having greater absorption strength, therefore it is present at the top of all the components as its individual band, and the species going to be eluted for the very first time is going to be least strongly bound species, and it is going to leave the column first. Then after elution of the least strongly bounded species from the column, all those intermediate species will be eluted, then finally the displacer will be coming out. So therefore, this displacement development will become very crucial whenever if we wanted to analyze, or if we wanted to do any separation, especially for the preparative work. So what are the advantages of this? Since we can load the chromatographic column in very high amount, every loading is possible, and we are least bothered about the fronting. Fronting is going to be one of the two non-ideal behaviors of chromatograms, so fronting and tailing. And if you overload the column, fronting is going to be the obvious thing. So if you go for displacement development of chromatograms, the overloading cannot be an effect. And even this displacement technique is very, very useful for partition chromatography, where the solutes are going to be partitioned between stationary and mobile phase. And the band density of the displacer will be more, therefore it will help to elute the solutes more rapidly. Therefore, the analytical time can be reduced by using a suitable displacer. So this is about the displacement development. On all these three are very, very important development of chromatograms. When we compare the performance efficiency of all these three techniques, we commonly follow elution analysis or elution development. We can say almost 90% of the chromatographic separations will be utilizing the elution technique, where we will introduce the sample to the chromatographic column. Dependent upon the relative partition ratio or distribution constant of individual solute, the solutes are going to be eluted. And in the elution analysis, the mobile phase will be introduced to the chromatographic column after the samples introduction, and the mobile phase will be carrying the solutes dependent upon the differential migration of the solute. Whichever the solute which is having lower differential migration into the stationary phase will migrate along with the mobile phase with rapid speed, and hence it will be eluted first. Then next to that particular solute, all other solutes will be getting eluted, and that is also dependent upon the differential migration of the solutes. So these are all about the development of chromatograms by frontal method, elution method, and displacement method. Okay. When you do any sort of chromatographic separation, what is the criteria to choose a selective stationary and mobile phase is very, very important. So let us discuss about the criteria for stationary and mobile phases selection. First, let me take stationary phase. Stationary phase, usually when we are going to use any solid stationary phase, particularly for gas solid chromatography or liquid solid chromatography or adsorption chromatography, an adsorbent is going to be a solid stationary phase, and that will be usually filled into the chromatography column. So what are the characteristic features of this adsorbent? It is very important. So any adsorbent if we use, it should not be soluble in the solvent what you are going to use it as a mobile phase. So if you use any solvent as a mobile phase, the adsorbent what you are going to use as a stationary phase, you should not react. Either it should not react or it should not be soluble in the solvent. And the stationary phase should have adequate mechanical stability. It should possess good flow characteristics and mechanical stability in the context of its non-degradable property, even when we go for analysis at temperature greater than 25 degrees Celsius. And even in GC, the temperature will be adjusted even up to around 500, 600 degrees Celsius. Therefore, we must be very careful while choosing the adsorbent. It should be mechanically stable and thermally stable. And because a series of components may be present in a sample which you are going to introduce to the chromatographic column, and the stationary phase or the adsorbent should have only interaction with the solute but not chemically react with the solutes. Therefore, it should be chemically inert. And the adsorbent what you are going to use must possess greater adsorption capacity. Therefore, all those species which are having a lower adsorbability can be eluted rapidly. On the species which are having greater ability to adsorb over the surface of the stationary phase, they can be retained by the stationary phase. And the nature of the adsorbent should suit the nature of the substance which is going to be adsorbed. Then only like attracts like principle will be holds good. If the nature of the stationary phase is matching with the nature of the substance going to be eluted, then a proper interaction between the solute and the stationary phase may be possible. And the adsorbent you are going to use must be inexpensive. Its cost should not be more. If it is expensive, because the amount of adsorbent we are going to use will be very, very high, certainly. Therefore, if it is costing more, then it will be impossible to bear the cost of this particular adsorbent. And it should produce reproducible and reversible results. Whenever you use this adsorbent, we must be able to condition this particular adsorbent, and whenever you use this adsorbent as and when required, the results must be reproducible. We must be able to recondition it. Say for example, some sort of interaction might have been taken place between solute and the stationary phase, and after the separation is over, we must bring back the chemical property or physical appearance of that adsorbent to its original state. That's what the reversible processes, very good for reproducible and reversible processes, the adsorbent should be. And its density should be higher than the solvent, because it should be settled in the chromatographic column. It should not have any flow with the solvent. Therefore, it should possess greater density when compared to the solvent or the mobile phase. And when we come to the liquid stationary phases, mostly used in gas liquid chromatography, where the stationary phase will be a liquid and a solid will be holding a liquid, and the outer surface of the solid will be having the liquid, and that will be acting as a stationary phase. This also must fulfill some requirements. What are those requirements? The liquid you are going to use as a stationary phase should be practically non-volatile and stable at the operating conditions such as temperatures, because volatile components will be separated by gas liquid chromatography, where the temperature will be going up to 500-600 degrees Celsius. So under this particular temperature, the liquid you are going to use must be non-volatile. It should not be converted into any ionizable species, or it should not be getting converted into ions, or it should not be converted into vapor or ions, etc. So it should be stable. So it should show selectivity for the components to be separated. So selectivity is very important here. If any stationary phase you are going to use is not selective, is less selective, then it is not going to be suitable. So selectivity is very important, and it should be reasonably compatible with respect to solvent. The compatibility with respect to solvent must be matched, because solutes are going to be separated based on the partitioning ability with respect to them. Therefore, the stationary phase what you are going to use must be compatible with the components. The solvent power of the components is also coming to the picture here, and it should possess low viscosity at the operating temperature. Operating temperature may be 25 degrees Celsius or 50 degrees Celsius or 500 degrees Celsius. The viscosity must be very low. If viscosity is increased, definitely the stationary phase is also going to affect the results. So it will become practically impossible if the original property of the stationary phase is affected by any of the experimental factors, such as temperature or mobile phase composition or something else, or property of the solute, whatever it is. If the stationary phase property is altered, then that particular stationary phase is not going to be ideal and it is unsuitable. So let us take some examples for these liquid stationary phases. Mostly they are commonly used in gas liquid chromatography, and these liquid stationary phases are categorized into non-polar, polar, intermediately polar, and certain stationary phases which will involve in hydrogen bonding, and some stationary phases are specific for some solutes. So first, let me take non-polar stationary phases. They do not have any polar groups. Say, for example, if you take polydimethyl siloxane, it is bonded between silicon and oxygen is further bonded with silicon. So this CS3 single bond O will be present n times, where n may be 6100 to 11500, and this is PDMS, a very bulkiest molecule, and this is highly non-polar. This is not going to have any polar interaction with the solute. So the average retention for non-polar solutes will be more when compared to polar solutes. So this is going to be the non-polar stationary phase. So polarity is decided by the nature of the substituents and the symmetry. Here the nature of the substituent is oxygen. Oxygen is present at both the sides, and even methyl is also present at both sides. So symmetry is appearing here. Symmetry is existing to this molecule. Therefore, because of the symmetry and because of the similar electronegative atoms attached to silicon, this is going to be non-polar. So this is going to be one of the important non-polar stationary phases. Even if you take a squalene is nothing but 2, 6, 10, 15, 19, 23 hexamethyl tetraicosane. It is having 20 carbon atoms. This is a aliphatic hydrocarbon which is substituted by methyl groups. There are 6 methyl groups have been substituted here. 1, 2, 3, 4, 5, 6. So tetraicosane, 24 carbon atoms are present here. So this is not having any either double bond or electronegative atoms such as oxygen, sulfur, nitrogen, etc. Therefore, this is going to be non-polar. So like this, many non-polar stationary phases we can use. Even modified silica can also be put under non-polar stationary phase, but the picture will be different. The scenario will be different for modified silica. Next, let us move on to polar liquid stationary phase. And these polar liquid stationary phases will be having highly polar groups, and they retain significantly polar solutes. The relative retention rate for the solutes which are more polar will be more when we use these polar liquid stationary phases. I can quote a couple of examples here. Dimethyl sulfolane, this is going to be dimethyl sulfolane. And sulfur and oxygen present here will be responsible for the high polarity of this dimethyl sulfolane. And even carbomax, polyethylene glycol. Polyethylene glycol, it has carried OH group. It has carried OH group. So polyethylene glycol, because of the OH group present, it is polar. So, and even the oxygen present here will make at the terminals, the oxygen present at the terminals will make this compound more polar. Therefore, this can be used. This is present in a liquid state, and this sulfolane will also be present in liquid state. Because of high polarity of these two compounds, they will be put under polar stationary phases, right? And certain intermediate polar stationary phases are also used for chromatographic separations, and they have low proportions of polar groups. The polarity is not highly extensive. They are intermediate between polarity and non-polarity with respect to property of these compounds, and they are suitable for the dissolution of both polar and non-polar solutes. Both the variety of the solutes are soluble in these intermediately polar stationary phases, but certainly they will have more affinity for polar solutes. Say, for example, if you take didecyl phthalate, this is going to be the structure of didecyl phthalate, and this is biphenyl. These are the two importantly used intermediately polar stationary phases. So these liquid stationary phases are intermediately polar. Both polar and non-polar solutes are soluble in these stationary phases. When you introduce a group of solutes which are polar, non-polar into the chromatographic column having this liquid stationary phase, polar solutes will be retained in the chromatographic column for longer time, but non-polar solutes will be eluted first. After the non-polar solutes elution, intermediately polar solutes will be eluted. So this is the order of elution when we use these intermediately polar stationary phases. And even certain liquid stationary phases which are very specific to form hydrogen bonding with solutes. Certain stationary phases will form hydrogen bonding with solutes, and this will become prime factor for the separation order. If any solute having the capability to form hydrogen bonding with the stationary phase, and the extent of hydrogen bonding will also decide the order of elution. So if you consider diglycerol here, the OH groups present here, right? And polypropylene glycol, this is going to be polypropylene glycol, tetrahydroxyethylene diamine, tetrahydroxyethylene diamine. So all these three compounds which are liquids in nature, because they got the ability to form hydrogen bonding, these OH groups present in this tetrahydroxyethylene diamine or hydroxy group present in polypropylene glycol or hydroxy groups present in diglycerol will become responsible to have the hydrogen bonding with solute. So intermolecular hydrogen bonding can be seen between solute and these stationary phases, and this hydrogen bonding will decide the extent or the order of elution. The extent of hydrogen bonding is dependent on the relative functional groups present, whether the hydrogen bonding between nitrogen and hydrogen or oxygen and hydrogen. So all these factors going to decide the order of elution. So these type of stationary phases are put under liquid stationary phases which have hydrogen bonding with solutes, and certain specific liquid stationary phases are also used. Say for example, if you take a solution of saturated solution of AgNO3 in ethylene glycol or glycerol or triethylene glycol or benzyl cyanide, so any one saturated solution of silver nitrate in either ethylene glycol or glycerol or triethylene glycol or benzyl cyanide, and if you use this stationary phase for the separation of olefins from paraffins, so silver ion will be coming to the picture here. Silver ion will be playing very essential role during the separation of olefins from paraffins. How it is going to play its role? Silver ion forms loose adducts with olefins rather than paraffins, right? So olefins will be having greater ability to react with silver to form a loose adducts. Therefore, olefins are attracted by silver, not the paraffins. So paraffins are eluted first, then olefins will be eluted last. Similarly, if you take any acetylene-like molecules, acetylenic hydrocarbons forms silver acetylene-like, and they will not elute out first. If you introduce any sample solution containing acetylenic hydrocarbons and other hydrocarbons, silver will hold acetylenic hydrocarbon compounds for longer interval of time rather than other hydrocarbons. Therefore, acetylenic hydrocarbons will be eluted at last compared to other conventional hydrocarbons. Even if you take tetracyanoethyl pentaerythritol TCEPE, this is also used as liquid stationary phase. Say, for example, for the separation of benzene from the hydrocarbons having 10 and 13 carbon atoms. So, benzene eluted out first when compared to C10 and C13 saturated hydrocarbons when we use tetracyanoethyl pentaerythritol, right? The interaction of benzene with this stationary phase will be lesser when compared to C10 and C13. So benzene eluted out first, so it can be separated from hydrocarbons having C10 to C13 aromatics. So therefore, the aromatic compounds can be separated by using such specific stationary phases such as TCEPE. So this is about liquid stationary phases which are non-polar, polar, intermediately polar. The liquid stationary phases which will allow hydrogen bonding, with the solutes, and some specific stationary phases which will react with the stationary phase or which will interact with the stationary phases with the solute molecules. Next, we shall move on to criterion for selecting mobile phase. We know gaseous mobile phase will be used as a carrier gas in gas chromatography, and liquid mobile phases will be used in liquid chromatography. So what are the requirements we have to consider for such a species in order to consider them as mobile phases? The choice of the mobile phase is very important because the successful separation is solely not only dependent upon the stationary phases nature but also the mobile phase condition or mobile phase composition or nature of the mobile phase or property of the mobile phase. So first, if you take liquid mobile phase, if any liquid you are going to use as a mobile phase, it may be a water or mixture of methanol, water, mixture of acetonitrile, water, mixture of acetonitrile, methanol, whatever it is. So whatever the mobile phase you are going to use, it should have common stability. Irrespective of the experimental condition, the mobile phase should be common. It should not undergo any fragmentation. It should not undergo any chemical conversion, chemical transformation. Therefore, common stability it should attain. And it should be compatible with the detector. If it is compatible with the detector, then only it will give one spike in the chromatogram. It is very important to identify the analyte peak. Dead time is very, very essential in order to find out the adjusted retention time and the retention index. Therefore, it should be compatible with the detector, and it should have adequate solvent power to the sample. The differential migration of the solute is dependent upon the property of the mobile phase. Therefore, it should have adequate solvent power with respect to sample. And when we go for sample recovery, it should not interfere. That means to say that when you look at the chromatogram, there must be additional peak for the mobile phase, but it should not be getting eluted with the solute molecules from the sample. So these are all the requirements we have to consider while choosing the liquid mobile phases. And when we choose carrier gas as a gaseous mobile phase, especially for gas chromatography, that gas particularly should be inert, because even this volatile gas, if we use this volatility matters there, it should be non-ionizable, it should be inert, completely inert with respect to physical property and chemical property, and it should be suitable for the detector to get detected to give a signal for this carrier gas or for this mobile phase, and it should perform well with desired speed. The analytical time is very important. So we must be able to complete the separation in desired speed. It must be with high purity. The impure substances which are present in the mobile phase also matters here. And when this gaseous mobile phase is moving through the chromatographic column, particularly when we use flame ionization detector, there will be a flame, and this gaseous mobile phase or gaseous species should not catch fire. So it should not cause any risk of fire, or it should not cause any explosion hazard. Such a high temperature we will be maintaining even under such a high temperature. This should not cause any explosion hazard. Such a gaseous species we have to use. And lastly, it should be cheaper. The cost of affording this gaseous phase is also very important. So these are all the requirements of liquid and gaseous mobile phases we have to consider in liquid chromatography and gas chromatography. Let us move on to the adsorption systems. And these adsorption systems I'm going to talk is with respect to solutes first. So when you go for a separation process or using any chromatographic technique based on adsorption principles, the relative adsorbability of the solute is going to be very essential. And this relative adsorbability is solely dependent upon the functional groups present. So the success of the separations is solely dependent upon the functional groups of the solute, not only the functional groups of the solute, the groups present in the adsorbent. Because adsorbent, you are going to use it as a stationary phase in adsorption chromatography, where the solute tend to undergo absorption in adsorption process. And so this absorption process depends upon the polarity differences between the solutes, and this is going to decide the order of elution. So say for example, if you take any symmetrical compound such as carbon tetrachloride or benzene, they are completely non-polar. Carbon tetrachloride or benzene are non-polar. So they don't have any adsorbability over the surface of any adsorbent. Suppose if you use silica as a stationary phase you are going to use. Silica is more polar, alumina is more polar, cellulose is polar, starch is polar, talc is polar. So if you use these polar stationary phases or polar adsorbents, these non-polar species such as carbon tetrachloride or benzene are not going to show any retention. So they will be eluted more rapidly. So all those symmetric compounds in the sense, if there is a carbon, if carbon is attached by similar atoms such as chlorine or hydrogen, right, the molecule will become non-polar. So molecular symmetry will bring the non-polarity to the compound, and all these non-polar compounds will show lesser adsorbability over the adsorbent. So these solutes are non-polar solutes. Okay, if you alter these symmetric compounds, say for example, N-pentanol if you take, N-pentanol is more polar when compared to N-pentane. C5H12 N-pentane, it is non-polar because the same atom hydrogen has been attached to carbon. Hydrogen atoms attached to carbon are similar with respect to electronegativity, therefore this will become non-polar. So one hydrogen has been substituted by hydroxy group, and this hydroxy group will become responsible to alter the polarity. So non-polar N-pentane become N-pentanol, and which is polar, which is more polar. So C5H11 OH is more polar than C5H12. Similarly, if you take benzene, benzene is non-polar, but nitrobenzene is more polar. The substituent nitro group will become responsible to alter the polarity of benzene. So benzene is non-polar when compared to nitrobenzene. If you take carbon tetrachloride and chloroform, one chlorine has been substituted by hydrogen, and this dissimilar atom substitution to the carbon alters the polarity. Therefore, chloroform will become more polar when compared to carbon tetrachloride. Of course, even chloroform is also less polar. So the polarity is going to be increased by the attached functional groups. So functional groups will decide the polarity of any molecule. So not only the molecular symmetry, but also the functional groups which are present in the molecule, which are present in the compound, will also decide the polarity. So based on the nature of the substituents and based on the nature of the functional groups present in variety of the solutes, how the adsorption ability of the solutes can be ordered, and that is presented in this particular order. The order of increasing strength of adsorption is presented here. If you introduce the group of solutes which are alkanes, ethers, esters and ketones, the adsorbability of the ketone will be more when compared to esters. Esters will be more adsorbable when compared to ethers, then alkanes. So when you introduce a group of compounds having alkanes, ethers, esters and ketones to a chromatographic column which is having silica as an adsorbent, as a stationary phase, alkanes will be eluted first, alkene will be next, ethers next, esters and ketones at last. Because the relative adsorbability of the ketone is more when compared to alkanes. So alkanes are going to be first eluted, then ketones will be eluted at last. In between, this group of compounds will be eluted. This polarity is dependent upon the functional groups. Alkanes, they don't have any functional group attached, just like benzene. Just like benzene or N-pentane, the alkanes have only carbon and hydrogen. They don't have any double bond. Even so, absence of the pi bond in the alkanes makes these compounds less polar or non-polar. Even alkenes have double bonds. Because of the double bond, the polarity of alkenes will be more when compared to alkanes. And ethers, because of the electronegative oxygen presence in ethers, they will become somewhat polar. But esters or COO R dash, if you consider, where R and R dash may be same or different electronegative species attached to carbon. So the polarity matters here. Ketones, if you take RCO R dash, ketones, even aldehydes, if you take, the polarity is dependent upon the substituent. Therefore, polarity is more for ketones than esters, then ethers, then alkenes and alkanes. Then next comes alcohols, amines and aldehydes. Aldehydes are less polar than amines. Amines are less polar than alcohols. So among aldehydes, amines and alcohols are more polar. Amines are less polar than alcohols. Amines are more polar than aldehydes. And this is all dependent upon the substituents to the carbon atom. So which is the functional group substituted to the carbon atom? If two or more same substituents are attached to the carbon, then that compound is going to be less polar when compared to the polarity of the compound which is substituted by different functional groups. Then phenols and acids, RCOOH, if you take any carboxylic acid, RCOOH, because of the OH group, and oxygen will be carrying double bond with the carbon, C double bond O, single bond OH will make the acid carboxylic acid to become more polar. But phenol, if you take C6H5OH, only one substituent will be present. Only oxygen is the differently electronegative species attached to the carbon. And because of the molecular symmetry, phenol will be less polar than the acids. So this is how you can imagine, you can predict that what is the order of elution when we introduce the sample containing solutes among alkane, aldehyde, amine, ethers, esters, ketones, etc. Okay. When we come to the observability of the solutes with respect to stationary phase context, so even stationary phase property is also very important. When we do separation based on absorption of the solutes, we need an adsorbent as a stationary phase. So what kind of adsorbent we will be using? The adsorbent will be in any highly polar solid. It will act as a stationary phase. Any highly polar solid such as silica gel or alumina or charcoal or starch, whatever it is. So any solid which is highly polar, which will act as adsorbent, and it will create an atmosphere in such a way that the adsorption sites of this polar solid will be welcoming the group of solutes to interact with that by hydrogen bonding. So if you take silica gel is nothing but SiO, at the terminals OH groups will be present and oxygens will be present in silica gel. SiOH groups are known as selenol groups. These selenol groups will become responsible. The selenol groups will become responsible for initiating the hydrogen bonding with the solutes. Therefore, this silica or alumina will become more suitable stationary phases for the retention of more polar solutes. So they will not hold, they will not show any affinity for non-polar solutes or intermediately polar solutes because of extension of hydrogen bonding will be very less. Therefore, you can decide the order of elution among more polar solute, intermediately polar solutes, and non-polar solutes while we use a polar solid as an adsorbent. Even alumina will also attribute to the same, but water's presence will be mattering here. So if you consider silica gel, the selenol groups will become responsible to initiate the hydrogen bonding with solutes which are more polar in nature. So more polar solutes will be eluted at last. Non-polar solutes will be eluted first, and intermediately polar solutes will be eluted in between non-polar and polar solutes. The same scenario can be seen when we use alumina also. Alumina will also attribute the polarity as same as silica. But if water is present, the polarity will be altered. So the order of adsorbents among alumina, charcoal, silica, gel, calcium carbonate, starch, cellulose, etc. If you put, this is going to be the order. Alumina is more polar than charcoal. Charcoal is more polar than silica gel. It is more polar than magnesium carbonate, then calcium carbonate, talc, starch, sucrose, cellulose, etc. So therefore, this is the order of specification of the adsorbents, and based on this order, we can choose which is going to be the most specific or selective adsorbent for the separation process, right? So most commonly, silica gel will be used as adsorbent because its property, we can reproducibly bring that to its original state to even after the separation is over. So these are the different adsorbents we will use in adsorption chromatography, where the partitioning of the solute takes place based on adsorption. So if water is present, the activity, the relative activity of these compounds will also be disturbed. So it is better to make these adsorbents free from water, because water is also highly polar. Water is also highly polar. If you consider silica gel without water, and if you consider starch with water, starch will become more polar than silica gel. So this is how the polarity will be affected in the presence of water. So these are about some adsorption systems with respect to stationary phases. So this correlates. The relative adsorbability of the solute is not only dependent upon its own property, but also the relative property of the stationary phase. If the stationary phase you are going to use is having more adsorbable sites, then the relative retention of the solute over the surface of the stationary phase will be more, right? Then we shall move on to the next bit of topic of this particular module is applications of chromatography. So there is no need to say much about this, because chromatographic techniques are always very popular in both qualitative and quantitative analysis. In qualitative analysis, we will use standards to identify the peaks, first of all. So we will use standards, we will run the chromatogram, and we will compare the retention time of the standards with the solutes eluted from the sample. We will compare the retention time and we will decide whether the solute is present or not. So comparison of retention time between standards and the sample species will give us certain hint about the presence or absence of the expected species in the sample. Say for example, if you wanted to analyze snake venom, so you run the suspected compound from the snake venom as a standard, obtain its retention time, and you introduce the snake venom directly to the chromatograph instrument, and you obtain the retention time. Compare the retention time of the standard and the species eluted from the snake venom, and similarly whether the blood is containing any metabolite or not, you have to inspect. So what metabolite you are expecting, take it as a standard, run the chromatogram, obtain the retention time, and you run the blood sample in the same process under the same experimental condition, under the same chromatographic conditions, obtain the retention time, compare the retention times for the standard and the blood sample. You can decide whether it is present or not. So this is about the qualitative analysis. And even the chromatographic techniques are very popular for quantitative analysis also, and they are highly sensitive when compared to any classical or instrumental techniques. So most commonly in quantitative analysis, the calibration methods using external standard will be used, where we will run the chromatogram, we will obtain the peak area or number of theoretical plates for standards of known concentrations, right? So you will generate the chromatogram by running the chromatographic separation for standards. You will elute the standards, each and every known compound of different concentration of the same standard you will elute. Of course, with increase the concentration of the standard, there will be increased peak area or number of theoretical plates. You will record it. Then you take the sample which is contained with the compound same as the standard, record the chromatogram, obtain the peak area or number of theoretical plate, plot the graph of concentration of the standard versus peak area or number of theoretical plate, then obtain the concentration of the analyte graphically. So this is known as calibration method, and this is of course true even in all instrumental methods where we will use calibration methods by using external standards. And even we can use internal standards. For quantitative analysis, we will use internal standards where we will compare the ratio of peak areas between internal standard and unaligned, and we can obtain the concentration of unaligned. You mix the internal standard with the sample is containing the unaligned. First you run the internal standard, obtain the peak area, then you run the mixture of internal standard and unaligned, compare the peak area and obtain the ratio between peak areas of internal standard and unaligned, then internal standard. You can find out the concentration of unaligned. So here you will compare the ratio of peak areas between internal standard and the unaligned. What is the peak area for internal standard? Separately you will have it. And what is the peak area of internal standard in the presence of unaligned? Right? So you can subtract the peak areas from the mixture of internal standard and unaligned and only internal standard. Then you can have the peak area for unaligned and you can calculate the concentration of unaligned. So these are some applications I can give a hint. And when we go to a specific discussion on gas chromatography or liquid chromatography or supercritical fluid chromatography, we will have more discussion on the quantitative analysis or qualitative analysis. So this is about application of chromatography. So in this particular module, we have discussed about development of chromatograms by illusion analysis, frontal analysis, and displacement development. And we discussed about the requirements for stationary and mobile phases for chromatographic separation. We discussed about relative observability of the solutes and order of elution of the solutes dependent upon their relative polarities, and the observability of the solutes over the surface of the stationary phase is also very important, and this has also been discussed under the head of absorption power of the stationary phase. So thank you very much. We'll see you in the next module.